Aloha. Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm pleased to serve as the coordinator for the Shadow the Scientist initiative. Shadow the Scientist is housed under the Creating Equity in STEAM umbrella of programs offered by our team at the University of California, Santa Cruz. Tonight, we have the privilege of shadowing the observing team at the International Gemini North Observatory. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on mountains in Hawaii and Chile, which enables the telescopes to collectively access the entire sky. Gemini Observatory utilizes Q observing mode, in which science staff take observations on behalf of science teams from all over the world. The staff determine the conditions on the ground and in the sky, as well as the scientific priorities, and choose from a pool of scientific programs to observe. In this session, the observing team consists of Brian Lameau and Matias Rodriguez. They will be using the Gemini North telescope located near the summit of Maunakea on the island of Hawaii, with the observations taking place remotely from the control room and the Hilo Base Facility. Our guide on this cosmic journey will be Zachary Harmon. Aloha, Zach, and welcome.
Hey, welcome everybody. I'm happy that we're able to at least hold this session now, where we had the chance of observing, but as we'll be talking about in a couple minutes, well, actually, I mean, I can just show you right now. So so right now we actually have high humidity, and we also have some clouds kind of right on top of the observatory. So this is actually using Keck's cameras, which are down the summit. So actually in the bottom right here, you can see Gemini right in the second telescope from the right. So unfortunately right now we are closed. And if that wasn't enough, we also, Kilauea, the volcano that's a little bit to the south of Maunakea, has erupted a little bit last weekend. And so let me see if I can find, let's see if I can find it. There's a great picture we had of the volcano appearing on, here we go. All right, download documents. There we go. Of the volcano showing up. And so this was actually a couple days ago. The black dot in the middle on the lower part of the Big Island is where Kilauea erupted, or where Kilauea is. And so and this was actually I think this was from the GEOS satellites. And so this was a screenshot by one of our SOSs here, Sonny Stewart. And so you can see this black dot there that normally is not there. And so the particulate count is pretty high right now. I don't have the numbers in front of me, but I think Brian does. So we're kind of just in a holding pattern, waiting for the particulate count to drop and the humidity to drop as well. So that's unfortunately where we're at. And so I know, Brian and Matthias are just kind of chilling in the control room. So if they want to introduce themselves, that would be great.
Sure, thanks, Zach. I would be happy to. So hi, everybody. I'm Brian Lamo. I'm one of the Gemini North staff scientists here tonight, hoping to operate the telescope. So I am what we call here at Gemini North an observer. So that's my role for the evening, which means I take care of executing the plan. So we have a staff scientist during the day that makes a plan. Jamika mentioned that we have a bunch of different observations that we could choose from. We make plans for every single different type of weather. And when I get to the telescope, I have all those plans in place. And my job is to juggle all of the instruments, all of the plans, assess the weather, and try to determine how we can get the best science out for the conditions that we have. And unfortunately, as Zach mentioned, we're closed right now. So we had shifted the session to tonight, thinking tonight would be much better than the previous night. The last night was very bad. We didn't open up the whole entire night. And unfortunately, tonight's starting off to be fairly similar. Zach showed pictures from the Keck cameras. The sky is actually gorgeous right now. We can see it also on our cameras here in the room, except for a few clouds. But the humidity and the high particulate count is keeping us closed. So I am very eager to open. I would love to do some observing, but unfortunately I have an operator here who is in charge of the telescope safety, and he's telling me we cannot do it. So that's Matthias. So Matthias, you want to introduce yourself?
Sure thing. Well, thanks, Brian. And that's correct. We can open right now because of the current weather conditions. Well, my name is Matthias. I'm an SOS, which stands for Science Operations Specialist. Right now, I'm on my duty as an operator, so I will slew the telescope to each target as Brian tells me where to go. But unfortunately, because of the weather conditions, we must keep it closed. Yeah, that's pretty much my job for tonight. But as a science operations specialist, we also could be the observers and pick up all the targets from the list of observations for the night and decide where to go regarding the current conditions. So, yeah.
So it's nighttime here in Hawaii, and so we're on what's called the night crew. There's usually two of us unless we have somebody training. So we have an operator every night, we have an observer every night. As Matthias said, he can act both in the operator and observer role. I'm not trained for the operator role, so don't trust me with the telescope safety. So I work on the kind of science side, getting proposals ready, getting projects ready to get to the point where they can be observed, and then to be here at the telescope at nighttime to ask Matthias nicely to slew to different targets. But we have a whole set of scientific staff that make the job possible. Zach is also an observer on occasion. He coordinates the queue, meaning that he sets up all these plans for observation in a given night. We have people that go up to the summit of Maunakea to get the telescope ready during the day. We have software engineers, we have hardware engineers, a whole group of people that get us ready so that we're in a good position to take scientific observations at the time. So all these crews did their work today. Telescope is in good shape. So the second things look good on Maunakea, we're ready to open. All of our instruments are available, and we can start taking some scientific data. So we have a special guest with us tonight. Do you want to introduce yourself, special guest?
Yeah, I can. Hey, my name is Finn Giddings. I'm an astronomy grad student at the University of Hawaii at Manoa at the Institute for Astronomy. I'm just here, just checking things out. I work actually with Brian on some different research stuff, so just visiting today. I'm just in town, yeah.
Thanks for joining us, man.
Appreciate you having me, yeah.
Yeah, so seeing as we actually only have a couple of people online for the grad students, do the two of you want to introduce yourselves?
And you're absolutely welcome to do so in the chat at any time while we're talking, or just raise your hand, no problem. We could maybe start talking about some of the aspects of observing, and then maybe if you guys have questions, you're welcome to ask at any point. Please feel free. The session is for you guys, and so anything that you're interested in, please just let us know, and we're happy to talk more about it.
Yeah, and I mean we're as Brian said, this is a session to show you all what we do at Gemini. And in particular, I mean, if you have any questions regarding general Gemini operations beyond observing, what our daily lives are like here at Gemini, feel free to ask those. Because I mean, we can talk all we want about what we're doing or what we can do with the telescope right now. But ultimately this session is for you all, and if you want to hear more about how daytime checks go, or what our jobs specifically entail, we are down to answer those.
Yep, I second that. So yeah, please feel free to ask any questions in the chat or raise your hand, and you're welcome to ask them verbally. We would love it if you guys introduced yourself at some point, or your scientific interests, or if you want to ask us about how we got here to this observatory and why we're doing the things we're doing. We're happy to answer those questions as well. But why don't we take people through some of these screens, Zach, because there's a ton of screens here, and we can take a little bit of tour of that.
Yeah, so if we were to, I don't know, so we're going to stop sharing. And so Brian, Matthias are in the control room. So if I can do this, you can see that we have a bunch of different monitors in there. And so typically the observer sits on the right side of the room. The SOS sits, the systems operations specialist sits on the left. And so normally there's
relegate any graduate students to the corner.
All of our weather information are on the screens on the front up there. So you can kind of see our sky cams that we have here. You can see a cloud kind of showing up in one of ours. You can't really see the top screens, but those are also weather. Those contain our humidity sensors and different seeing measurements, cloud cover, water vapor, and a bunch of other stuff. But so I'm going to walk you through what Brian would normally see. So I'm going to stop this pin. And so I'm going to now I'm going to share the screen again. So this became 10 times more complicated when we were cyber attacked the other last year. So okay. Let me see if I do it. Yeah. So this is one of the screens that Brian has. And so on the screen, I'm actually going to start with this screen down here, actually. So this screen contains, basically the big one is this big giant TSD, or telescope systems display. So this gives you a bunch of information about the telescope status. It shows you where we're pointing, different mechanical values, different instrument offsets, because the light is, if you just fed the light directly into the telescope, it may not end up correctly where you want it. And so we have instrument offsets to align the light to where we need it to go. It has the local serial time, the UT time, in the on the bottom here, you see different display screens for the telescope itself. So on the left, you see the dome, and if we were open there, you'd see the silhouette of a dome with an open dome cover. But for the moment, we're pointed at zenith, and the dome is shut. Same thing with the screen, or with the light path of the telescope, which is the second to the left figure, or wait, first from the right figure. And so you can see there's this kind of shaded out part of a light path on that figure. But you can also see that we currently have the dome, that we currently have the mirror cover locked, or shut, because you can see this black jagged line here. But then below that, you see a bunch of different instruments, or a bunch of different numbers. And these correspond to the different instruments. So the way Gemini works is it has an instrument cube at the bottom of it. And so a lot of these may be familiar to you. We have GNIRS, which is our infrared spectrograph. You have GMOS, which is our optical workhorse instrument. So it does imaging, long spectroscopy, multi-object spectroscopy, and IFU. The AO is ALTAIR. This is our AO system. GCal is where any calibrations, like if you have arc lamps or stuff like that, the light will come from GCal. At the bottom is visitor. And so right now, MAROON-X is on the telescope, so that is our visitor instrument. And then in GCal as well, you have Alpaca, which is our speckle camera, and is another visitor instrument. And then actually, if is this cut off by my screen, it's cut off by my screen. So on the far right here, you have these 4 boxes in the lower right corner, and these represent our wavefront sensors, our guiders. So whenever we acquire on a target, when you guys are setting up, when you all are setting up the phase 2 in your program, most of the time the programs will be set to find an automatic guide star. And so that's what is grabbing for this operations, because basically these sensors will stare at that guide star and provide some corrections while also keeping the telescope pointed. And so OI is really only used with GMOS, P1 and P2. P1 is not really used anymore, but P2 is used with a lot of different instruments. So if you all have used GNIRS, that's where P2 comes into a lot of play, and so along with Alpaca and MAROON-X. And then GMOS really uses OI. And then we also have our AO wavefront sensor, which right now is really used with GNIRS, although it used to be used a lot with NIRI. And so that can be either used with a laser or natural guide stars. And so if I go to the other screen, okay, it's still up. So if I go to this screen back here, this screen shows.
Hey, Zach, you may want to go to screen 3 or 2. I have an example of a GMOS observation of a standard star with, yeah, there you go, with the OI. So just to get a kind of visual of it.
Stop. So yeah, so in the OT, if you go into the image display, it will show you your object, and will also show you the guide star selection. So as Brian was mentioning, this is a selection for OI, where the green and red dashed box kind of shows where the OI field is, where it can find stars. And then the blue, cyan blue diagonal going across the middle, that represents where the slit is going to be for the long slit spectroscopy. So that really represents the area for OI. P2 actually goes between, well, it would go between, but Brian has covered it up. It would go between the outer green circle and the inner dashed line. So you can see these dashed lines going about, going around the target. And so, like, for example, Brian's showing this right now. This is technically an okay guide star, but it's also vignetting the image or some of the spectra. Sorry, there's a bug flying around me. I'm sorry, but termite, you have the die. All right, there we go.
I thought we agreed to no killing, Zach.
The termite was bothering me. And so you can technically go with this, but you would have some vignetting in your image. So traditionally with P2, it's kept between the inner dash circle and the outer green line circle. And so yeah. But when we see it at the telescope, what we see is a couple different things. So when we're guiding on a target, if you focus on the upper two plots at the top, this is the values of the astigmatism and tip tilt that we're getting from the wavefront sensor. I mean, right now it's 0 because we're not guiding on anything. But if we were guiding on a target, you would see it varying up and down. And so it would be trying to take that into account as it was guiding, at least a little bit. We don't have a full adaptive secondary yet. That's actually in the works. But for the moment, it's good enough to take some small corrections into account as we're observing. And then the other plots here are useful for us as we're going throughout the night. So you can see, if you look at the left two plots in the bottom there, you have the middle one is OIFS seeing graph, and that shows a measure of the seeing based on the guide star. So this would give us an idea of what the image quality is. In case, we have a program that wants IQ 20 weather and we're in IQ any, we don't do that one, obviously. And then the bottom one is just showing the counts that we're getting hitting the guide star. And then so the other two on the left-hand side or on the right-hand side are weather information. So you can see here, and I wonder if Brian can click the either RH1 or RH2 just to bring up that.
Sorry, what was that?
Do you want to click on the weather RH1 or RH2 on the plot?
For the units.
Sure.
Yeah. So you can see that so the orange and the red, or the orange and the pink, show the relative humidities that we get that we're getting right now. And you can see that they are pretty high, like 90%. And so for us, we close at 85. And then it has to drop below 75% humidity and stay there for an hour. So right now it is doing the opposite of what we want it to do, which is rather annoying. But this is how observing goes. And so there are a couple other things in here as well. There's temperature, there's wind speed. And you can see that sometimes the wind is, and the wind is actually shown in better detail down on the bottom plot. And sometimes the wind is getting very high, and sometimes it's kind of very low. And so right now we don't have a good measure on it because the dome's closed, so we don't have that wind speed for us. So those are kind of the two weather things. So I showed you screen 3, which is where Brian is keeping the OT. So screen 2, Brian here shows us two important things. So number one of the jobs of the observer is to keep track of the night log. And so we have a scientist here who made a very useful Python script, which takes the Q plan that our QCs, our Q coordinators, have made and puts it into a text format. And so we're able to go in and we're able to basically take this and put it into the night log. A lot easier than having to manually type it out. And so then behind there, you see our sec exact. That's where when you all put when you all put a program together in the OT, you have contact scientists and they're making sure that everything is working or everything is good in the program, so that what happens is when we queue that program in the OT or through the OT, it shows up in the sec-exec, and then we just execute it through the sec-exec. So that's why the contact scientists always are double checking everything, making sure everything's good, because observers at night trust that this program is set up correctly. And so we just load it in and we automatically just run it. And if it isn't, and if that is not the case, then it runs into errors, and then that leads to data not being taken and time being lost. So that's happening on that screen. I'll just pull up this in case it's different. So this is the OT again. And so so this is the OT, and as you can see, Brian has a library or has his own workspace open in the background there, with a lot of different observations set up, so that for contact scientists in particular, we can go in and we can be like, all right, how is this, if we have a question on how a program is set up, we can be like, okay, how was this actually set up before? And we can go in and look at previous observations and be like, okay, this is how it's supposed to be set up. Here's what we need to do to get it to work. So let's see here. So this is the queue plan for tonight. So every single day, there is a person at Gemini who goes and makes a queue. Well, multiple queues. We make one for every single weather condition that we think is going to be that is going to be potentially possible. And so you can see on the left-hand side that there are 10 plans. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 3, 3, 2. No, it is actually 10. Or 11. It's 11. 11 plans, taking into account different weather conditions. And so by basically, this allows the observer at night to not have to make up new plans on the fly. So if, say, we're observing and it's really good conditions and the clouds are gone, and then suddenly the clouds roll in, we can switch plans very easily without having to burden our observer and operator by having them make up a plan on the fly. And so someone does this during the day, and that can take anywhere from 4 to 8 hours to do in a given day. And so it's a long process, but ultimately it helps out the observatory to have all these plans. And hopefully in the coming years, we'll have a fancy code that actually makes the plan for us. At least that's what I was told when I first got the Gemini, and it's been 3 years now and we don't have it yet. So we'll see whether that comes into fruition sometime soon. Although Brian is getting trained to be a QC, so we'll see how much fun he has with that.
That'll be a great time. Thanks, Zach. Katya, do you guys have any questions about that? We have a lot of information that we're throwing at you, so please feel free to ask us questions at any time. If you see something that's unfamiliar, or you see, I guess you guys are maybe starting to look at the observing tool at some point with your collaborators. So, I mean, if you have any specific questions about how any of this works, we're very happy to talk you through it.
Yes, please interrupt me.
So I see Katya is doing GMOS IFU in one slit mode for galaxies. So that's yeah, maybe we could bring up a program at some point for that. IFU is it's usually reasonably easy to do in the observing tool, but it definitely has some complicated.
Yeah, please either put them in the chat or just let us know and we can unmute you and have you ask questions. Because I mean, that's mainly I think I've shown most of the observing screens. Hopefully, as I said, we'll be able to get on Sky at some point during the next hour and a half. Because one of the things that one of the big parts of our jobs on the observer side is when we go to a new science target, we have to acquire on that target, and show, and that is a particularly it can be really good, or it could be really bad, or not bad, but really long and complicated. So it's definitely a process that is really interesting to see happen live. So yeah, I think that's it from the observer side.
Yeah, Zach, you maybe want to show the ISDs just for fun, since I guess at least so Katya has done some GMOS IFU, or at least collaborators.
Yeah, do you have them on a screen? I didn't.
I do, yeah. It's on 7 or 6, depending on how you're numbering.
All right, it's 7, or it's 6. So yeah, so the ISDs are the instrument systems display. So these are GMOS and GNIRS, and basically this shows all the moving parts that are going on in each instrument. And so if we were to set up on a new target, there would be a lot of flashing lights going on the given instrument display. And then once they get to their target, everything would turn green, like it is now. And if there was a problem, it turned red. For some instruments, it's a really fast exchange. But for others, it takes a little bit of time to get to move one of the slits to a different slit, or move a grating, or move from imaging on GMOS to IFU on GMOS. That all takes time. And so by having these up, we're able to kind of track what's going on and make sure everything's working well during the night on the observer side. So yeah, these are the ISDs. Yeah.
Yeah, I mean, so everything here at Gemini is configurable, and it's fairly fast, the configuration. So there's other telescopes on Maunakea like Subaru or Keck, and if they want to switch instruments, especially instruments, but if they want to switch configurations, that process can take up to 30 minutes. Subaru has a instrument called Hypersuprime Cam, which is an amazing instrument. It's a basically 1 degree radius imager, so it looks at 1 degree by 1 degree squared on the sky. But the filters for that instrument are like 3 or 4 tons a piece. And so if you just want to change from like the R band filter to the G band filter, for example, that movement takes about 20 or 25 minutes. In 20 or 25 minutes, we could reconfigure to like 4 different instruments, 3 different settings on GMOS, take like 5 different observations. And so we're very fast, very agile. And these screens that Zach's showing right now help us keep track of all the different configurations. So a lot of the telescopes still on Maunakea are classical observing, where you are dedicated, you apply, you and your team either come to the telescope, or you observe from Hilo, or you observe remotely from in your pajamas at home. But you're given a certain night. The conditions are whatever the conditions are. You either get the telescope open or you don't. And you take your observations with your single instrument. And so usually, not a whole lot of switching is needed unless something goes really wrong with the instrument that you're planning on using. I've been on Keck before where I was going to use an instrument called GMOS, which is a multi-object optical spectrograph. And all of a sudden during the day, the coolant leaked on GMOS. And so I got to the telescope and they're like, surprise, you have to use a different instrument. And so we had to struggle and try to figure out what are we going to do with a near infrared cross-dispersed spectrograph that's a single object versus a multi-object optical spectrograph. But that doesn't happen very often, luckily, that people spill coolant all over the place. But so you come to the telescope, you're given the conditions that you have, and you take the observations roughly that you planned, or maybe you pivot a little bit, but all with the same instrument. with Gemini, we're doing community science, as you guys know, and so there's this big pool of programs that we have. We are contractually bound to take observations according to the condition constraints that are given in the observing tool that your collaborators or you set up when you first proposed for Gemini observations. And so we are always watching, is the sky, does it have more turbulence? Is the seeing worse than is required for this program? Are there clouds coming in that we're, we might need to take a spectrophotometric standard for the program that we took, an hour earlier? Is the moon rising? And so we need to shift over to near infrared observations versus optical observations. And this is where the configurability of Gemini, the agility of Gemini becomes really important. And so as Zach showed in the first screen that he was showing, which is the telescope status display, we have this, maybe you can bring it up again, Zach. Yeah, I think it's that one. Yeah. We have this tertiary mirror, which is this green flat mirror here. So I guess you guys can't see my mouse, but anyways, light enters from the top of this little picture of a telescope where this red thing is sitting up at the top there. So that red square thing is our secondary mirror. Light enters from the top. It bounces off our primary mirror when the mirror cover is not on covering it up. Bounces to the secondary, and then bounces to our Cassegrain instrument cage here. And this deployable tertiary mirror directs the light to any of the different instruments. And so Zach talked about this a little bit earlier. So we have these offsets. We want to make sure the light goes exactly where we want it. But just switching in between like GNIRS, for example, and tonight, one of the visitor instruments that's on is MAROON-X, which is a extreme radial velocity spectrograph. That process takes less than the time of a slew to another target. So basically within a minute and a half-ish, we can get the light piped to a different instrument and configured for that instrument to be ready for the next observations. So as Zach mentioned, this is the exciting part, or one of the many exciting parts of Gemini observing, because we slew, we switch instruments, we then acquire the target, we take the observation, and then we move on to the next observation. And so it's always changing, always dynamic, always different targets. We go from solar system to gamma ray burst to high redshift lens galaxies, back to the solar system to galaxy evolution, AGN, local AGN with GMOS IFU, then redshift 7, super bright quasars with GNIRS IFU, to extreme radial velocity transits of planets with MAROON-X, all in one night's observing. And I come from a classical background. I come from Keck and Subaru, where it's really lumbering beasts. We're just sticking on a target for 4.5 hours, not moving, just letting the telescope do its business, and getting the 10 photons that we need from the distant galaxy. So it's a very different dynamic here. And of course, I guess at least some of you know that we have a very good target of opportunity program. So we have programs that are dedicated for targets of opportunity, and principal investigators or the team that's associated with a given program can what's called trigger a target of opportunity almost any night they want to. And so at the observatory, if there's something exciting that happens, like a supernova goes off, or an interstellar visitor comes into our solar system, which may or may not have just happened. Contractually bound not to say anything, but which may or may not have just happened. Then people who monitor these things that have time on the telescope that kind of predicted that some of these things would happen during the semester, they say, "Ooh, that's super exciting. I want you guys to go look at that." And so then we get an alert here. And we then, depending on the priority, either slew immediately to that target and take some observations, or we wait, up to a week, depending if the target can handle that. So it's a very dynamic place to work, and at nighttime, nothing is ever sitting still, except for when we're closed, which we currently are. So even then, we're constantly monitoring the clouds that are that are coming in. The sky looks absolutely gorgeous right now. We're monitoring the humidity. So with the gorgeous sky, as soon as the humidity drops within acceptable limits, we'll likely open up and take observations. So we're just trying to get prepared for that at the moment, and be ready when Maunakea graces us with the opportunity. Unfortunately, as Zach's saying, it's not moving too much. So humidity is kind of flatlined at the moment at levels that are quite a bit higher than our opening limit. So it doesn't seem as though we have much chance of opening up currently, although it's predicted to be quite nice tonight. So hopefully the prediction comes true. And Pedro, thank you for joining us. If you'd like to introduce yourself, or if there's some questions that you have, please feel free to type them in the chat or raise your hand. You're welcome to turn on your video. Anything you like is just a few of us here, so feel free to have a conversation with any of us. And yeah, Zach's showing, I mean, absolutely gorgeous skies. This is what we're used to in Maunakea. This is why all the telescopes are here. It's absolutely gorgeous, lack of light pollution, usually really great wind conditions, not a whole lot of clouds. Just unfortunately tonight, the combination of the volcano belching the other day and humidity is keeping us away from that absolutely gorgeous sky.
Yeah, so the safe range is basically if it hasn't been humid, then anything below 85%. But as soon as it goes up above 85%, then we have to close the dome. And then after, if it drops below 75% and stays there for an hour, then we can reopen and resume operations. So unfortunately, it is holding at 90, so we are nowhere near that 75%. So yeah.
And then I guess, Matti, if it were to drop below 75 and stay there for a while, we would do a dome drain, right?
Yeah, probably not, because just today, during the day, the humidity was behaving pretty well, but yesterday we didn't open and we got a lot of high humidity. We reached 100%, a couple of precipitation sensors. So in that case, the scenario, we need to do a dome drain. That means to move the dome in a certain position and the telescope to a certain position and open the shutters of the dome in a way that if there's water in between the shutters and if it drops, it doesn't come into the mirror. So we need to follow that procedure. I wouldn't expect that much water right now, but if there is like a huge storm or Maunakea was hit by a lot of water, then we should expect a dome drain for like maybe an hour or something, waiting for all the water to come down and to be safe to open our mirror cover and observe the cosmos. So yeah. Unfortunately, as Zach said, humidity have been still at 90%. We can see from the cameras like the atmospheric waves reaching with the high humidity at summit level. But the sky looks clear. It's that kind of weird situation that you would love to be open and doing the best science in the world, but we need to be patient and just wait for it.
Yeah, so our goal is definitely to do this for years and years and years to come. So despite how tempting the sky is tonight, we want to be very, very careful with everything and move nice and slow so that, you know, if we don't get open tonight, this is one of the very nice things about Q observing. And for myself, coming from a classical background, you know, I would come to a telescope. I would fly from, when I was not living in Hawaii, I would fly all the way from Europe sometimes to come to Hawaii. And I'd be like, great, I put in this proposal. I'm super excited. I have all this science that I envisioned doing with the observations. I flew the 15,000 kilometers to be at this telescope this night, and there's clouds, and there's humidity. And then that's where you really need somebody saying, no, you can't open because we want the observers tomorrow night to be able to, use the telescope. And so, I would be like, come on, I really want to see these, observations go through, because it's maybe not another year before I get another chance, if I get another chance. But with Q observing, if we don't get it one night, depending on the observation, but if there's like something that has a really strict window of time that we can observe, well, maybe they don't get another opportunity. But for most programs, they get another opportunity the next night. So that's great. And if your program is highly ranked, if you apply to Gemini and your program is highly ranked, the chances that it gets observed in a semester are pretty dang high, which cannot be said for a classical observer. There is drawbacks of this type of observing, which is that you generally can't change the type of observations that you take, or let's say you discover a super exciting different kind of target for your science that since you've made the proposal, you can't just wantonly pivot to that target and say, oh, I want to go there. And that's a really cool aspect of classical observing. We may make the proposal 6 months earlier, and then our scientific perspective has changed over the course of 6 months. And we arrive at the telescope and we say, okay, great, we have some of that we want to do, but we also want to do this entirely different thing. And we're basically given the keys to the telescope for the night, and we can do what we want. Ooh, the Pedro's using Ghost, or he's intending to use Ghost. Zach, you're a Ghost expert, aren't you?
Oh, no, I'm not.
No, you're not? I thought you did the SD thing.
I did help with that.
Okay.
So, I know what it is. I've never used it. So, yeah, Ghost should be a good instrument. It will be a good facility instrument at Gemini South for a really long time. I hope to use it as well. So, it better be there for a long time.
And it's like extreme RV kind of stuff as well. It's like
no,
right?
No, it is high resolution. So there are two modes. It's 40,000 and 80,000 roughly. But it's not, we have an instrument at Gemini North called MAROON-X, which is built specifically as a high precision radial velocity instrument. It's very stable. In particular, it's not on the telescope. There's a wire which actually goes from the instrument cube down through the floor into the basement of Gemini, where the instrument actually is, which gives it more stability, and so it has a higher radial velocity precision, or it's able to achieve a higher radial velocity precision than Ghost is able to, as Ghost is on the telescope. At least I think it is.
So MAROON-X is what, like R of 120,000 or something?
R of 80,000, but because of its at least I thought it was R of 80,000. But as its main thing is that it's super stable in how it was built. So let me just double check, because I was pretty certain it was R of 80-ish thousand. Yes, R of 80-ish thousand, but because of the way it's built, because of the way it also has a laser frequency comb, so all the calibrations and the added stability of not being on the telescope leads to it having a much higher radial velocity precision than one might expect. So Ghost, while Ghost is going to be really good, the exoplanet community in particular is still waiting on the high resolution mode to get super stable in order to really do some fun exoplanet stuff with it. There's still a lot you can do with it, but to get like the real cutting edge stuff, you need to get that stability in the system.
There's no eidolon or laser frequency comb in Ghost?
No. Now the neat thing about Ghost is that it has the ability to potentially get 2 targets at once. So I mean, it has 2 IFU fiber bundles that kind of just you point them wherever you want, and you can get 2 targets at once with that. So
Nice. It's mounted to the telescope, right? It's not like a fiber fed thing.
I mean, it is. So the IFU, it's IFU fiber bundles, but I'm pretty sure it's mounted on the telescope.
Yes, it's actually unimportant.
That was my understanding of how it was supposed to work. So yeah, unfortunately, we're just kind of chilling here for the time being, waiting for the humidity to drop. You can see all the other telescopes have their dome closed too, unfortunately. So yeah, please let us know if there are any questions you have about anything at Gemini, not just related to what we're doing tonight with observing, but if you have any questions about proposing for Gemini time, about what life is like at Gemini, feel free to ask. Otherwise, I mean, I guess we could show, you don't happen to have an IFU observation in your workspace, do you, Brian?
I do actually. I brought one up from 22A
Right,
that wasn't observed.
How's it here? Over here. I'm assuming it's here. Yeah, so someone mentioned IFU. So this is an example of one of the IFU programs here at Gemini North that unfortunately was not observed. But you can kind of see how it's set up. So you have the IFU in the middle, and then OI is the guider. So that's the green and red square. That's the tracking area for OI. So yeah, I mean, it's a really, I mean, I like whenever we're observing with GMOS in particular, it's for the most part, unless your target is, super faint, it's a really easy acquisition. And a really easy observation because we just have to center the target and then just let the system go.
Yeah, so this is like a acquisition sequence for an IFU. And I guess when Zach says super faint, this would be fainter than 21st magnitude AB, something like that. So if it's brighter than 21st magnitude AB, it's usually okay. If not, then it takes a little bit more finesse. And our GMOS IFU is not like super sensitive. GMOS itself is very sensitive. The IFU is fiber fed, so it's not. There's some light loss through the fibers. So we normally, in an acquisition sequence, we take an observation without the IFU. So you can see, so this is our observing tool. And this is the thing that if you guys have done phase 2 or you've set up a program or whatever, if you've interacted with Gemini at all, beyond just with your collaborators, you probably would have seen something like this, at least in terms of observations. There's also the archive, which maybe, Pedro, you're pulling off some stuff from the archive. So this is our main observing tool. We use it to set up all of the observations. So we interact with the proposing teams. Once their proposal is successful, we make sure everything's set up correctly so that at nighttime we can execute those observations without too much brain power, because, at 3 a.m, you don't want to be thinking too much, or the least amount of thinking possible is helpful. And so we have 2 different sequences for this particular observation, and then that are taken during the nighttime, and then one that's taken during the day. And the acquisition and observation, we usually take, in fact, we always take an image of the location that we think the target is at. So if we were going to this target now, I would say, hey, Matty, do you mind slewing to this program, to this observation? And once we got there, we would make sure that we were guiding okay, everything was okay, we were in roughly the right location, and then I would start an acquisition sequence. And so I would start by taking an image of that part of the sky, and we compare it to what we expect to see. Hopefully we're seeing something similar. With the IFU out, usually a 30-second or 1-minute exposure. It's a big telescope. So, even things that are of 21, 21 and a half, we can pick those up pretty easily in a fairly short exposure with GMOS. As soon as we think we are in the right location, so I might make a few tweaks to the location, or actually I would measure the offsets that are needed to get precisely on the location of the target. And I would say, hey, Matty, I just sent you some offsets. And then Matty would make those precise adjustments, and he would say, okay, offsets are in. And then I would start again with another image. We'd confirm that we're in the right location, or we'd iterate. Once we feel like we're in the right location, what happens is the focal plane unit changes. So it moves from having no focal plane unit, so just straight up mirror, just piping the light into GMOS to the detectors, to moving the IFU bundle in. And so that's offset by several tens of arc seconds from the optical path. What is it?
30.
30. Okay. Yeah. So for the GNIRS IFU, it's 9 arc seconds. GMOS, it's 30. So there's a movement that's required basically to account for this offset. Then once the IFU bundle is in, we take a through IFU image, which is not dispersed. It's basically white light image. And we make sure that we see the target there. There's where things get a little bit sketchy, because the target needs to be reasonably bright for us to see it through the IFU. So there, in a reasonable amount of time, we might be able to pick up things that are 19.5, 20 in R. If it's fainter than that, we basically require a blind offset. So you pick an object that you feel like is bright enough to be able to see with the IFU in, and then you make an offset away from that. That's you hope you're measuring the distance between your target and the blind offset object well. And then once we take the through IFU image, so that's this last part of the sequence. We have a 60-second exposure for this particular target. We center it up in the IFU so that movement to the IFU can have a little slop with it. And so we maybe just make one little last adjustment, and then we say, okay, good, we're ready to go. And then we start with our science sequence. And so as soon as our science sequence starts, we would configure GMOS. And so this is where the IFU is already in, but we start to disperse the light. So we put in the disperser that is requested by the program team. So that could be, maybe you've heard of B480 or R400 or R150 or R831 or B1200. So these are all different gratings which have different sensitivities at different wavelengths and different levels of resolution. And so depending on the science that you are proposing for, so Pedro, I guess for your science, you would need a resolution of like 40,000 or 80,000. GMOS doesn't do that. So the best resolution that you can get is with the B1200 grading. And that's probably R of 6,000, 7,000 if you're lucky. So that, for most, like the science that I do, I look at like fairly distant galaxies between redshift like 0.5 and 5. So for me, actually lower resolution is better. So I just put in a proposal for Gemini for 24B that's looking at, I don't know if it's successful yet, so I'll find out in a couple of days. But it's looking at galaxies in a protocluster, a forming cluster of galaxies at redshift 4, where the objects are, well, our targets are anywhere between 21st magnitude AB in R and like 26th magnitude AB in R. And so Finn knows well, actually, how difficult these observations are. And so they're really having lower resolution. So we're actually using the lowest resolution grading, which is R150, where our resolution is like somewhere around 300 or 400. And we're basically just binning the photons along the dispersion axis, along the wavelength axis, as much as possible, so that we get a decent level of signal noise for a reasonable exposure time. And so even with that, our exposure times proposed were something like 3 hours or 3.5 hours. These are MOS masks, so we get 20 to 30 galaxies at a time, but still a pretty decent commitment. But if you were going for higher resolution, let's say you needed, so if you're looking at IFU observation, you're trying to get I don't know, different emission lines, for example, in H2 regions. So you need to separate out H alpha from singly ionized nitrogen, from singly ionized sulfur, from doubly ionized oxygen, And so there you would need a resolution around 3,000 to 6,000. So one of the lines that actually we looked a lot at for Finn's work, his initial work, was the oxygen 2 doublet. So this is at 3726 and 3729 rest frame. And so this is only a 3 angstrom separation. And for Pedro, this might not be much, but for these kind of low to medium resolution spectrographs, that's really you're starting to push the capabilities. And so anything with like the B480 grading, for example, wouldn't be able to resolve out these two lines. And so it might be like you propose a science case to Gemini and they say, cool, that sounds good, but listen, you're using the wrong disperser. So maybe you want to shift over to the B1200, for example, if you're really trying to resolve out this oxygen doublet. And that would be like one of my jobs to say to people, hey, cool proposal, you got accepted, everybody thinks it's a good idea, but technically it's not totally sound. And so let's change things around a little bit to make it better. So for the IFU observations here, we put in one of these dispersers depending on the science, and then the light would go from being direct light, so like basically 0th order light, to first order light, so the actual dispersed spectrum. And so you get the spatial resolution from the integral field unit, looking at, in this case, what is it? So it was like looking at the toroidal region around a black hole. So probably looking at ionization states and outflows and things like that. So gas kinematics. So you get that spatial resolution, and you'd also get the spectral resolution that was required for whatever science you were doing. Matthew, did you do some like IFU stuff? You were doing Lyman continuum escape stuff, right?
Long slit.
Long slit, okay.
Yeah, for ionized gas kinematics.
Yeah.
Yeah, not that far.
It was like the Lars survey or something like that? Low redshift, like analog?
Yes, low redshift Lyman continuum survey.
Yeah.
So a few observations with the LTX shooter and others with the ISIS.
Yeah.
With Herschel telescope. Like 10,000 resolution.
Yeah.
It was
10,000, really? Okay.
Yeah,
So, okay.
it was pretty fun.
Yeah.
Yeah, you can see a lot of kinematic components on the spectra.
Yeah,
It's
10,000, you can start to do some
Yeah.
damage, right? Yeah,
yeah. It's fun.
because there, like beam smearing really matters, right? Like if you have lower resolution, then you start mixing together a bunch of different
Exactly, as with
velocity.
the nitrogens and the
Yeah.
H alpha. And our goal was to try to investigate and check the broad components on the wings, the
Yeah,
the low signal.
right. So you both need high
components, so
resolution
you need-
and
exactly you
yeah,
need
and high signal to
high
noise.
signal to noise and resolution. So you need to figure it out what to do.
Yeah.
And it will be great now to kind of the same but with IFU
Yeah,
to have a spatial idea of how are the alphas.
HRIFU, GNIRS.
Yeah, who knows?
Who knows? So Pedro asked a question. Proposals are split in bands 1, 2, 3. How is it calculated the band of the night, and how is it decided to change from proposal of band 1 to band 2, for example? Okay, yeah, good question. So the band is assigned actually by the time allocation committee. So there's a group of scientists for each country, each partner country, that get together and they read proposals anonymously, like meaning it's dual anonymous. You don't know who's reviewing your proposal and they don't know who you are. So that we take out any human element of it. And well, as much as we can. And then they say, yes, this is a really awesome idea. Yes, this is an awesome idea, but not as awesome as that other idea. And this one, it's like, okay, but it's maybe not that cool. Oh, this one is terrible. Like we don't think that that's a very good idea. And so like the pressure factor, meaning the number of hours that are asked for versus the number of hours that we can actually accept, depends on the partner country, but it's anywhere between like 6 to 1 and like 1 to 1. So maybe only 20% of the proposals that we can accept. And so the time allocation committee says, here's the 20% that are all pretty dang good, but some are like a little bit better than others. And so we're going to give those that are a little bit better, we're going to give them band 1 status. We're going to give those ones that are very good, but not the best, band 2. And then we're going to give ones that are still really good, but we don't really have any time, much more time available in like the really high leverage science time. We're going to give them band 3. And then band 4 is you can propose basically any time, honestly. It's poor weather observations, but if you have a good project that's for like cloudy skies or where the turbulence is high in the atmosphere on the ground layer, you can actually get a lot of really good observations that way. And that can happen at any time. And so we do that process for each country. Then there's an international time allocation committee that tries to balance, all the time available between the different partner countries, tries to figure out, okay, in a given RA range, do we have, a nice distribution of targets for, we know that 50% of the time it's absolutely photometric on Maunakea, and then 50% of the time it's not. Are all of the proposals that are accepted require like spectrophotometrics, like clear conditions? If they are, then well, that's not feasible. So let's enter in some programs which are still good ideas, but didn't quite make the cut, but don't need these like super crazy photometric conditions. And so they put that all together, and then the final ranking comes out, and that process is happening right now for 24B. And that'll be determined in a couple days. And then at that point, you're stuck in your band. So that's you can't like say like, hey, no, but it was a really good idea. Like, no, please move me up to band 1. What you can do is you can propose. So let's say you get band 3. Band 3 is hard to get. I mean, like the observations can happen for some programs, and sometimes there's kind of a weird phase space, especially in some semesters with bad weather, where band 3s actually do much better than band 1s. But generally band 3s are hard to get. They're deprioritized quite a bit. So what you can do is you can say, okay, well, I didn't get any time that semester. I got, band 3 time. It doesn't seem like they're taking my observations. Why don't I propose for fast turnaround? And fast turnaround is a program that happens every month where it's peer review, distributed review. So you can propose, you review other people's proposals. If you're successful, within 15 days or so, you can actually get observations. And those are again ranked in band 1, band 2. There's no band 3 in that case. And so there's a variety of different ways of proposing and potentially getting, observations through different avenues. So I don't know if that totally answered your question, but on a given night, we choose the highest priority observations where we rank by bands. So the TAC tells us these are the best ideas. So when the conditions are the best, we try to fill those nights with band 1, and if we have to, band 2 observations. When the conditions are not so good, usually band 1, band 2 require fairly good conditions. So when the conditions are not so good, then we start seeing more band 2, band 3 observations, band 4 observations when conditions are crap, when it's cloudy, when the image quality is very bad. Those are almost exclusively band 4 nights. So I've seen band 4 programs come in and they've gotten their observations within all of their observations, which are tens of hours within a week or two. And so there's a lot of opportunity there. I don't know if that answered your question, Pedro, but.
Yeah, it sounds like they're having fun times with cameras. So if like we've been saying, keep the questions rolling. We have about 30 minutes left for right now. In this session, as we mentioned before, it's unfortunate that we're not able to open due to the weather conditions. But hopefully there will be another time where you all are able to see what's going on in the control room when we're actually observing.
Yeah, well, I'll just say we have these Shadow the Scientist. This is not the only time we do Shadow the Scientist. We do these sessions very regularly. I think actually we have another one coming up on June 11th. And so if you guys want another opportunity to watch us observe, it's on the same website that you registered for this session. It's a public session, so anybody's welcome to come, and you're welcome to sign up. And usually this time of year is much better. I mean, Matty and I got snow the other night. I mean, this is not normal for Hawaii. I mean, it does snow on Maunakea. That's why it has the name, but that usually happens in the winter, not 2 weeks before the summer solstice. So this is not normal. And my guess is that unless this crazy year continues up into the solstice, right abreast of the solstice, that we'll have a pretty decent chance of opening up on June 11th. And if that doesn't work, we have another public session on July 22nd, where we're going to show off Migrants 2, which is our newest, just about to become our newest facility instrument. There's a science verification run that's happening then. And we'll be doing it about once per month, roughly. We'll be having public sessions. So you guys are always welcome to come and watch us observe. Either I'll be here, or Zach will be here, or somebody will be here. We'll just make Finn come again.
Maybe I'll be here, yeah.
Maybe Finn will be here. But we have different staff observing on every night, and everybody has different backgrounds. So you're welcome to ask them about their backgrounds, not only the science, but also the humans involved in science.
Yeah, I will say, I mean, so we're not only holding this program right now for all of you who have applied for the GNIRS visitor program, but I mean, even if you apply again and you still don't get it, if you're ever in either La Serena or Hilo on some other observing run, like hopefully maybe you get time on Keck Observatory, or you get time on SOAR or any of the other telescopes located in either location, I mean, feel free to contact anybody at Gemini. We're happy to have visitors there. We're happy to bring people in. If you're coming in anyways, and give a talk or meet the staff there. So again, just please keep us in mind as you're if you're going into either location. And we'll be happy to set stuff up for you. But yeah, I mean, if you have any questions, let us know. I mean, there's some nice satellites going through the images right now. So, or from the Keck observing point of view, or the Keck camera's point of view. So,
Katya, Mizna, Pedro, would any of you feel comfortable just like explaining your science or your interest in Gemini, maybe in the chat or verbally? We'd love to hear about it. All the graduate student visitors that have come here, that applied to the program and successful. They've met all the staff. We've talked science. They've given talks, and that's the wonderful part about this program. And so, unfortunately, you can't be here in person, but we'd be very happy to discuss with you your science or your interest in Gemini.
Can you hear me?
Yes,
Yep.
we can.
Here in Brazil is 4 a.m., so I speak a bit lower. So what we tend to do with the ghost is because we are studying the Hawai Nebula region. In my master thesis, we studied the open cluster NGC 1981, and what solved on my dissertation was that he's passing through some disruptive process. So, but we have much problem to identify his members. Because of that, we use the GA data, and what we saw is that we need mainly the metallicity and the radial velocity to better assign the membership. So with the goals, we intend to do this to improve this membership assignment, and also to analyze the interstellar major components, because we have some B stars in NGC 1981, and we try to understand the region has in a complete way, because it's the main focus of my thesis. So what we are trying to do is to get a better understanding of what's happened on the clusters on the region, and try to understand a bit more about the star formation history on the horizon.
so would you be using the high resolution mode or the low?
The low, because to improve the efficiency, because we need to observe the B stars, the hotter stars, and the fainter stars, because the one thing that's most important is to determine the metallicity, and for that we need the FG key stars from the cluster. So we kind split the observation, the proposal in these two ways. One, it's the observing of the bright stars, and The second part is the observation of the faint stars. And now we are kind of try to get more data. We are searching for other spectras like in the Apogee to complement our data. I qualify in these years, so I think the ghost data will be if our proposal was approved. I use my thesis, but not in my qualification, probably.
I'm just trying to think. I mean, so for using,
Hey,
uh-oh,
no,
there's a visitor. Yeah, I was just thinking, like, I mean, so for the ONC, I mean, how faint are the objects that you're going to be looking at?
In the proposal, it's Gmag of 13, something
Okay.
like that.
So could you compare this with the I'm just wondering, like, how much information you can get from the Gaia, just from the calcium band triplet data that Gaia has. Like how good, like comparing those two sources, the ghost and the Gaia rate of velocities and their metallicities that they derive from that.
What's the resolution of that?
So the resolution on the calcium triplet from Gaia is around 20,000. So I mean, Ghost definitely is going to do better. I'm just wondering, like, I haven't messed with the Gaia rate of velocity stuff that much, so I'm just wondering, like, whether or not how much, like, metallicity information you can get from that directly.
And that's one point, because many of the sources don't have the radial velocity termination on Gaia.
Oh, really? Okay.
And I think that this region of Orion is one of them. So, but when I worked with my dissertation was the R2. So we didn't use the radial velocity because at the time it wasn't available. So now we will looking for the radial velocity from Gaia, and we have to try. And from the Apogee data, we also have the radial velocity termination, and we
Okay.
use it. We try to use the Gaia, but I think the data of Gaia will not support on this because the resolution, and I think it's not determined. But besides that, the goals will help to the ISM components too. So we are trying to looking everything we have on the region. We have this astrometric photometric information from Gaia. We try the spectroscopic data from the ghost, and we have some regions covered by planimetric in the LPD. So we try to understand, we try to get the data we have of the region and try to understand what's happening with the clusters mainly.
And you can reconstruct the star formation history of this region just based on the metallicities and the, I don't know, the kinematics, or how exactly do you reconstruct the star formation history?
That's our guess, because if like one thing that is interesting in this region is because NGC 1981 it's 1 degree north from the Orion Nebula, and he's close to 5 million years old, and below it, like 20 Arc minutes, that is an 1977. That is other open cluster that is younger than 1981, but he's embedded yet. So what we think it's happened there, and kind of some part of the literature say that too. It's a sequential star formation that in 1981 it's formed first, then with his feedback events, he ignited the star formation process on in 1977. And if you can distinguish between the members, if you can see a difference in the metallics, for example, in the radial velocity, we can try to see if that really happened. So we can reconstruct part of the history of the region. We don't know how much we can reconstruct. I think that is the point.
No, it sounds like a really interesting proposal.
Are there any evidence of like shocks in that region, or would they have already died off by the time that we've observed them? I mean, you said 5 megayears or so, the age?
Yes. Not close to the clusters. There is a hot bubble, the Orion Eridneus bubble in the region, but it's far away from the cluster. In the region, the evidence that we have is that the bright stars of the NGC 1981, they very they have a great spectrum on the astrometric data. And if we analyze only the photometric data, they were considered as members of the cluster. So there is something happen in this cluster, and if it is one example of a cluster that is going through some disruptive process, so we can try to understand what causes this process and how the cluster evolved through, not only the history of the region.
And Pedro, this was a 24B proposal, so is that right?
Yes.
Okay, so you'll find out in a couple days with me.
Yes.
Exactly.
we tried to submit to 24A, but the horizon is very low in the sky, so
Yeah.
the proposal was not accepted. But to
What,
try again, we improved the proposal and try now for 24B.
What condition constraints were you asking for?
Band 3.
Band 3, okay. Okay, so
Because
we're not...
it's spectroscopic data.
Cool. Well, good luck. Hopefully, yeah. I know the people on the ITAC have been working very, very hard. We see them wandering around the halls with a vacant look in their eyes. So at all hours of the day and night. So I think they're getting very, very close to making an announcement sometime in the next couple of days.
Yeah. Hopefully next week. I think
Next
they were saying they wanted to get it to everybody like partner wise this week, and then
Okay.
I think probably next week.
Okay, Monday morning.
Yeah, Monday morning emails. Yeah.
Well, thank you for sharing. That was
Yeah,
great.
very interesting.
You're welcome. I appreciate very much to talk about.
Thank you for doing it not in your own language and at 4 a.m. That's that's very impressive. Appreciate your commitment. And I see Katya just put something in the chat. So they said we are studying compact massive galaxies at redshift 0. Used open data from SDSS and Subaru to study stellar population and morphology properties. For our research, we're interested in Gemini observations, investigate stellar population properties, kinematics, IMF, dark matter fraction. Most of our galaxies have already been observed. So we started to work with the data. That's really awesome. Katya, if you don't mind putting in the chat or verbally, it would be really interesting for me to know how you measure IMF or how you constrain the IMF using these data. This is something that we always worry about at high redshift, changing IMF, varying IMF, the consequences of that. And I know it can be done at lower redshift, but I'm not super familiar with how that is done. Okay. Okay. So G is modeling. And so all the observations have already been taken with GMOS IFU. Did you use both GMOS South and GMOS North? Or I guess it's SDSS data, so probably mostly in the north. Yay, we win.
Yeah, that's something that now that we've built up a huge amount of data on the archive, we're hoping that that gets used more and more. Because there's a lot of data just sitting out there on that archive, just waiting for people to dig into it.
Just out of curiosity, how compact are these and how massive are they? Are they like 10 to the 12 solar masses or 10 to the 11? And do they sit like in clusters, or are they mostly just like isolated galaxies that for some reason are very massive? I realize this is a lot to type out, but this is like partially my field, so I'm just curious. We just had a journal club today on massive galaxies at high redshift that turned out not to be massive galaxies at high redshift.
What, a solar mass?
What's that?
A solar mass? Is
Solar mass at high redshift. 10 to the 11.7 and above at redshift 3. And with 6 hours of MOS-fire data, my postdoc proved that they were actually lightweights at 10 to the 11.2 at redshift 2.5. So 1 to 1.5 kiloparsecs effective radius and stellar mass greater than 10 to the 10. Yeah, so super, super compact, and fairly massive. High mass density. Yeah, yeah. So GWST is starting to find things that are fairly massive. One of the staff members here today was showing me a paper from GWST where there was a really nice near spec spectrum of the rest frame ultraviolet at redshift 14. And it was a 10 to the 10 solar mass galaxy at redshift 14.
Look, I'm just
Very
happy.
compact.
I'm happy with my 0.5 solar mass stars within 100 parsecs.
That's very cute.
Yeah, I know you all can have your massive galaxies and
You know, galaxies are made up of stars.
yeah, but I can't study those stars in other galaxies now, can I?
No. In Andromeda you can, I guess.
I don't know.
Roger
I've been
does
having a large discussion with another postdoc about whether or not Gaia is of any use for them.
Okay, okay. You can get the bright stars in Andromeda.
Those are too massive.
Yeah, I'm sorry. You're very needy. So Jamika asked us a question about whether or not we had been a part of the graduate student visitor program as graduate students.
Or a program somewhere, I think.
A similar program as graduate students, and whether or not that was useful. So Zach is one of the founding members-ish of the graduate student visitor program. Did you have an experience?
I mean, I guess I did actually, now that I think about it. My first grad school observing run So not my first one overall. My first one overall was at Kitt Peak, but different telescope. My first grad school experience was it's not directly like related to the program, but through Noir Labs, like, well, through when it was NOAO, and I guess I think it's still continuing now. If you're a grad student working on your thesis and you got time on one of the mid-scale observatories, so the 4 meters that are available in the US, you could apply and get money to go to the observatory and take your data.
Oh, nice.
So I did that with the Wind telescope at Kitt Peak. I went and I actually visited Tucson and gave one of the flash talks there.
Nice.
And yeah, it was a really great experience. And I mean, definitely in the era of big data, as we're getting more and more used to just downloading large data sets off a computer and working with those. I think being able to come to an observatory, see how the data is taken, how each of the different jobs builds into how making the observatory run, and getting from A to B in terms of proposal all the way to data on my laptop. How that's done, I think, is a very good experience. And you meet a lot of people who may end up being, on hiring committees that you're attending, and
Yeah, so actually so I didn't do a graduate student visitor program. This didn't exist where I was at.
I don't think grad student visitor programs really exist.
Yeah.
Anyway.
Yeah, I mean, it sounds like NOAO had like a little bit
It
of a
was
thing.
an observing thing.
Yeah.
It was the main part.
Yeah.
So
but my undergraduate advisor was nice enough to take me along for the ride for some observations at the Keck telescopes. I think I observed, let's see, 5 nights total on the second Keck telescope when I was an undergrad, and my undergrad advisor was actually the person who started the Shadow of the Scientists program, Roger Guatakurta. And basically I remember him throwing me in the room. He had just come back from where was it? It was a meeting or a conference in New York. He was like severely jet lagged. He showed up at like 6 p.m. flying from New York to Hawaii, and he said, "I'm just going to take a quick nap on the couch, and then why don't you go ahead and take the controls of the telescope." Luckily, as Zach said, I mean, there's so many cool people at the observatories, so many people that are willing to help, that are willing to show you how to do things. So at Keck, there were support astronomers there. They're super awesome, super professional, and guided me through my trembling hands through all the necessary movements for observations. Luckily, I'd done a lot of preparation and studying beforehand, so I felt some level of confidence in the observations. And I think we had gorgeous nights. I had some very famous, they weren't famous at the time, but very famous astronomers that were observing with me that are now on many hiring committees in different places around the US and around the world. And that was a tremendous experience. It was so cool to take those observations, feel the pressure of the observations, eventually succeed under the pressure of those observations, get the data, analyze the data. And I had been using, for my undergraduate thesis, I had been using data from the same telescope, same instrument, that other people had taken observations for. And this was my first time actually going from preparation stage to this was MOS observations, so getting masks aligned, taking the data, analyzing the data as it came out, to quality assess. Do we need more time on this particular target? Can we move on to the next target? So on and so forth. And the level of respect that I gained for those observers, all the data that I had kind of analyzed before, but nonchalantly thinking, okay, it's just data that comes from somewhere. I don't know where it comes from, but it looks nice. That's fine. To actually being like, wow, this is really tough. It's amazing that everything works. So that I can do my silly little undergraduate thesis. And since then, I've observed on CAC probably like 150 nights, and it never like ceases to amaze me. Well, first of all, how everything works, and how you get this incredibly large telescope, get this little pinhole field of view where the light pops through and goes into your instrument and lands on your detector, and you get your 5 photons that you wanted to get after 4 hours of observation. You say, yes, I've got my science out of it. It's spectacular, Zach. Five of them. We don't even have to speckle them. Yeah, so I think I mean, if you guys have the opportunity, certainly go to another telescope in your region. We're hoping to continue this program, so in the future, please do reapply for the program. Again, you're welcome to come to any Shadow the Scientist session that's public, and so I mean, it's a poor substitute for sure for being at the telescope, but we here are observing remotely. We're not on the top of Maunakea. We are down at basically sea level with a connection up to Maunakea, and of course something is lost by that. We're not sitting under this beautiful sky. Hilo is one of the rainiest places on Earth, and so it's probably raining outside. Statistically speaking, it's probably raining outside. But we're observing remotely, and we can bring that experience to you through Shadow the Scientist. So I will mention that it's not only Gemini that does Shadow the Scientist. It's Keck, Lick Observatory. My group's going to do some on Subaru coming up in the winter.
Chara.
Yeah, I mean, there's just tons of opportunities, and it's not just limited to astronomy as well. There's a bunch of other scientific disciplines that are open for people to watch, so to experience, not to be a part of. So please do take advantage of that. And thank you guys so much for joining us. I mean, I know it's crazy late, at least in or early or whatever in Brazil.
Yeah. We had the early morning session. I saw you were connecting from Brazil, and I was like, oh my goodness.
Yeah, we're gonna be doing another session, what, in
5 hours?
5 hours from now. So we're here no matter what.
Yep, we're here. So if you want to come back for that one, and maybe we'll be observing. So
yeah, the sneak preview is that if we do get open, we're going to be doing some crazy asteroid chasing. That we have an observation that's planned for later tonight, which is the craziest observation I have ever attempted. So
it's gonna be fun.
It's going to be crazy. Yeah, I'm gonna. We'll have some fun if we're open.